Okay, let's move to the next topic. So, which is basically covers the diodes and its applications. Applications. So, during this couple of slides, we basically covers the rectifier diodes, the concept of rectifier diodes, because they are the mostly common used set of diodes. We call it as general purpose diodes. So we first start with the rectifier diodes and try to understand the concepts behind this, and then we apply those theories and concepts to explain the simple circuit which may contain rectifier diodes. So then step by step we move to the Zener diodes, then the voltage regulators and so on. So I believe that you have a kind of a fair knowledge about the construction of the diode. So during your physical electronic module, I believe like you basically cover the implementation of this P and N type of semiconductor materials by using these doping technologies or techniques. So by introducing different type of impurities, you can easily make this N type and P type semiconductor materials. Then you can have a kind of a p-n junction by simply plugging this p and n type semiconductor materials. So for this particular section, we are not uh, explain the concepts or implementation of p-n junction and its properties. So we simply start with the diodes and try to explain the behaviors and the impacts, how they operate in different scenarios by using the properties of the diodes, not this p-n junction. So actually this discussion is not covering the material level discussion about the diodes and p-n junction. So we immediately start with the characteristic of the diodes and use these characteristics to explain the behavior of the circuits. Okay, so then once you go through the slide set which I shared already, so you can see some information about the how we can implement or how we can make a p-n junction using this P and N type of semiconductor materials. And again, like we know that the how this P and N type of material induce the electrical current using the free electrons and holes. So once you combine these P and N type of semiconductor materials together, so you can simply observe a kind of electron or hole movement across this uh, junction between P and N semiconductor material, and come into a kind of a stable scenario. So then you can see like how once we apply a kind of a voltage across this P and N semiconductor material, or else we can simply say that the once you apply a voltage across P N junction, what happens to the P and N type of material or the free electrons and holes. So we can basically apply voltages like we can apply a positive voltage and we can again apply a kind of a negative voltage as well. So so we are not go through this material level discussion, but we'll simply jump into the characteristics of the diode. So the characteristics basically impose, like we are basically interested about the VI characteristic. VI characteristics. So V represents the voltage and I represent the current. So we are interested about the voltage and current characteristic, or how, what happens to the current or the behavior of the current when you apply a voltage across this PN junction. So once we comes to the diode, so we know that it's a kind of a PN junction. So diode itself is a kind of a PN junction. So this is a p-type material, this is a n-type material. So we basically identify that this is the positive terminal of the diode and this is the negative terminal of the diode. Or we can simply say that this is the anode of the diode and this is the cathode of the diode. So we can represent this diode or a PN junction using this kind of a symbol. So this is the representation of diode in most of the circuit. So we can have different type of symbolic notations depending on the textbooks you are referring, or sometimes depending on the um, type of diode. So basically rectifier diodes can be symbolized like this. So then this is the positive terminal of the diode and this is the negative terminal of the diode. See, like you can see a kind of a K here. So this is K. So this K represents the cathode. So this is your negative terminal and this is your positive terminal. Okay, so the direction of the current would be like this. So this is the current flow and this is the voltage drop across the diode from minus to plus. So we can simply say that, so this is the voltage drop across the diode and the current flow through the diode is to the direction plus to minus sign. So we simply denoted these two quantities by VD and ID. ID is the current flow through the diode and VD is the voltage across the diode. Okay, so then again, like so we can power this diode. So this is your diode. So we can power this diode like this. So you can connect a voltage source like this. So this is the positive terminal of the diode and this is the negative terminal of the diode. Once you connect the positive terminal of the source to the positive terminal of the diode and negative terminal of the source to the negative terminal of the diode. So this is the one way of connecting external source. So the second is like this. So we have diode. So we can connect the source in the other way around. So positive and negative. Yeah. Okay. So in this case, we basically connect the positive terminal of the diode to the negative terminal of the source. Plus to minus and minus to plus. Here plus to plus and minus to minus. So this is the way we can easily apply the voltage by changing the polarities of the source we connected. So this is this scenario, that the way we connect the source is defined as forward bias. So this is called reverse bias. So there are two uh, ways of connecting the external source. One is you can connect the source to make this diode forward bias, and again like you can connect the external source to make this diode reverse bias. So this is the different is like in this case we are just connecting the external source uh, to the diode like plus to plus and minus to minus, so plus to minus and minus to minus. This is the simple way of identifying that, but later on you can see that there may be a kind of a different mechanism to identify whether the diode is forward or reverse. But for the time being we'll just assume that once you connect the external source to the diode in this manner, so diode make it forward bias. Once you reverse the polarity, diode make it reverse bias. Okay, so then you can see like the voltage drop across this diode is like this. Here again, so this is your VD. What happens in this case? So once you apply Kirchhoff voltage law, we can simply say that the voltage drop across the diode is exactly equals to the source voltage. So there won't be any other voltage drops across the circuit. So we can simply say that the diode drop or the voltage drop across the diode is exactly equals to the voltage of the external source. For this case, so we can simply say that the diode drop is equals to the minus of the source voltage. Once you apply the Kirchhoff voltage law, we can simply say that the voltage drop across the diode is equals to the minus of the source voltage. So we'll try to understand the characteristic of this diode. So this is the voltage, so this is the current, so the current. So we can simply identify two regions. So where you have like plus voltages and minus voltage. So once you apply a plus voltage, there will be a current flow through this device. So this is the current. So we can treat it as a positive current. So then, so this region, so we call this first quadrant as the forward direction of forward bias region. So we'll put like forward bias region. And once you apply negative voltage, we know that the current flow would be into the negative direction. So this would be like, so this is actually reverse bias region. Okay, so the forward bias region and reverse bias region. So when the current and voltages are in positive, so you can simply identify this first quadrant as the forward bias region, and this voltage and currents are in negative direction, you can simply identify this third quadrant as the reverse bias region. So once it comes to the characteristic curve, it's something like that. So this is the characteristics of the diode. So once you apply this positive voltage across the diode, and if you increase the diode voltage of the source from 0 to a kind of a plus value, positive V value, So once you increase your source voltage from 0 to a kind of a positive voltage, so you can see like, so there won't be any current flow through the diode once this diode is connected to a 0 voltage. So while you increase the diode voltage, you can simply observe that there's a certain threshold voltage. So once we increase your source voltage beyond that threshold voltage, you can observe a kind of a current flow through this diode. So once you apply 0 voltage, or let's assume this is a kind of so VK, so this is the knee voltage. So this is the knee voltage. This is actually the yeah. So this is the knee voltage. So once you increase the source voltage beyond that knee voltage, so you can observe a current like this. So once you increase the voltage, so the current flow through the diode is getting increased. But keep in mind, like in the practical diode, once you apply a 0 voltage, you can't see any current. So you have to apply a voltage which is greater than VK. So if the applied voltage across the diode is greater than or equals VK, so you can see a kind of a current flow through the diode. Otherwise you can't see any current flow through the diode. So once you map this scenario to the material level discussions, you can see like, so this current is basically due to the majority carriers. So this current is basically due to the majority carriers of the diodes. But once you apply negative voltage across the PN junction of this diode, so then the current is very small. So this is actually like if you apply a voltage less than 0, so you can't see a current. Let's assume like you can't see a current, but also so you can see a current in a microampere range. It's a very small current. In this case, it's a milliampere range. So in this case, the current is actually in microampere range. So it's a very small current flow through the diode due to minority carriers. Okay. So once you apply a positive voltage which is greater than the knee voltage, you can observe a current in a milliampere range. Otherwise, the current is simply 0. Once you apply a negative voltage across the diode, you can't observe a kind of a notable current, but there is a kind of a very small current in microampere range due to this minority carriers. And here, so at a certain point, once you increase the negative voltage apply across the diode to the negative direction, it means like your diode is now in reverse bias region, and once you increase the reverse voltage across the diode at a certain point, so this diode get breaks. So why? So we know that once you apply a negative voltage across the diode, due to this negative potential, the depletion region of the diode getting increased. The width of the depletion region gets increased and increased. So once you increase this negative or the reverse bias voltage up to a certain level, so then this expansion of this depletion region cannot tolerate anymore. So at a certain point, your diode get break or it's burnt out. So that is the maximum reverse voltage which that particular diode can tolerate. So that voltage is actually defined as a peak inverse voltage. So this particular voltage is denoted by the term called peak inverse voltage. So the peak inverse voltage is actually the reverse bias voltage. Keep in mind it's a reverse bias voltage which this particular diode can tolerate. So it's the maximum reverse bias voltage which this particular diode can tolerate. So this is the characteristic curve. So we identify a couple of information. One is actually we know that this diode is basically operating first quadrant and the third quadrant. So the first quadrant is identified as a forward bias region of the diode, and third quadrant is identified as a reverse bias region of the diode. So once you apply a positive voltage across the diode, when this applied voltage across the diode is greater than the knee voltage, so this is actually this knee voltage equals to the barrier voltage of the diode. So once this applied voltage is greater than the knee voltage or the barrier voltage of the diode, so this you can observe a kind of a reasonably high current which is in milliampere range. So at the same time, once we apply the negative voltage across the diode, we know that diode now is in reverse bias region and there won't be any kind of observable level of current. So you can, once you connect a very precise measuring equipment to measure the current, you can see a kind of a microampere range current which is actually due to the minority carriers of the PN junction. So then ideally we can simply say that the current flow through the diode when it's become reverse bias is almost zero, almost zero, almost zero. And so during this reverse bias region, what happens to the PN junction is that the depletion region gets wider and wider. So when we increase the reverse bias voltage beyond a certain limit, that expansion of depletion region is so cannot be tolerated anymore. So at a certain point of that, so you can simply see that the diode get burned, so it simply breaks up. So this the maximum reverse voltage which diode can tolerate is defined as the peak inverse voltage. So this is the peak inverse voltage. So that's why this current is like just jump to infinity. So it means like once you apply this voltage beyond that peak inverse voltage, so you can see a kind of a notable current flow through the diode. It means like it's simply short circuit, so you can't use the diode after that. So then once it comes to the forward bias region, you can simply say that this the supplied voltage should be greater than or equals to this new voltage Vk. Otherwise you cannot observe a kind of a notable current flow through the device. So then by looking at these characteristic curves, we can simply identify two regions. One is actually the voltage supply or voltage applied to the diode should be greater than or equals to Vk. So this is called ideally, so you can see a kind of a diode current. So you can ideally say that now your diode is in forward bias region. So once you apply a voltage which is positive voltage which is greater than the knee voltage or equals to the knee voltage, you can simply argue that the diode is in forward bias region and you can observe a kind of a milliampere range current or a kind of a current in a notable magnitude. So if it is less than Vk, so the diode current is actually zero, and you can simply argue that the diode is in reverse bias region. Okay, so this is the two conditions which we need to make the decision, or which we can take the decision about whether the diode is in forward bias or reverse bias is this. So if the applied voltage or the applied voltage across the diode is greater than the knee voltage of Vk, so V is greater than or equals Vk, so we can simply claim that the diode is in forward bias direction, and otherwise the diode is in reverse bias direction and you don't see any current flow through the diode. So this is the condition which we need to trigger when you decide whether the diode is in forward bias or reverse bias region. Okay. So then again, like we can characterize the curve. This is actually, so we define, this is the VI characteristic of the diode. So this is the VI characteristic of that. So it's something like that. So this is the VI characteristic of the DAM. So we know that so we basically use this first quadrant or the forward bias region most of the time, but for the certain cases we use the reverse region as well. But for the rectifier diode, keep in mind we are dealing with this forward bias region only most of the time. But once you consider the Zener diode, so we are basically using this third quadrant or the reverse region to make this Zener diode in a kind of a usable manner. So for the rectifier diode, we basically use the forward bias region for the most of the application. So this is forward bias and this is the reverse bias region. So we basically identify two regions: forward bias first quadrant and reverse bias third quadrant. And again we identify two key parameters, Vk and peak inverse voltage. So Vk, or the knee voltage, is the actually this barrier voltage of the PN junction. So we know that once the applied voltage is greater than or equals to this barrier voltage or the knee voltage, we can see a current flow through the diode. Otherwise you can't see any current flow through the diode. So these are the two conditions that needs to be satisfied when it is in forward region or reverse region. So keep in mind, if you want to analyze the diode, whether this particular diode is in forward bias region or reverse bias region, so these are the condition you need to check. Whether the applied voltage is positive and which is greater than or equal to Vk, so we can simply claim that the diode is in forward bias region. So if the voltage applied across the diode is less than Vk or a kind of a negative value, we can simply argue that so it should be like reverse bias. So you can simply identify this as well, like for the germanium type of rectified diode, so Vk would be like 0.3 volt, and silicon type of diode, so we can simply say that the Vk is equals to 0.7 volt, or this gallium arsenide, so the diodes which are made from gallium arsenide, this Vk would be around 1.2. So these are kind of known factors, so most of the time so we are using these diodes, silicon diodes. So then the knee voltage is 0.7. So depending on the diode, we can identify they have come up with different values of peak inverse voltages. Okay, so then we can mathematically characterize this curve. So once it comes to the mathematical modeling of this curve, we can basically model this forward bias region using Shockley equation. Shockley equation. So the Shockley equation can easily map it to this curvature. So this, so you can see that the in the slide set, So we can model this forward region using Shockley equation, the diode voltage, saturation current, emission coefficient. So based on these parameters, diode voltage, saturation current, and the emission coefficient, and the thermal voltage. Basically, based on these two a couple of parameters, you can see a kind of a relationship between the diode current and the diode voltage. So we can simply model this mathematically using this Shockley equation, which is a kind of a exponential type of equation. So if you want to precisely analyze the characteristics, so you can use the Shockley equation to find the diode currents for different diode voltage. But for this particular section, we are not dealing with this much of precision. So we basically want this actually, so whether the diode is in forward region or diode is in reverse region, and then we identify a couple of models, diode models, to explain the scenarios. Like we don't need to have this very precision values, very precise values. So we can basically use these diode models to explain the behaviors and identify what kind of output would be there. So then rather sticking to this Shockley equation and find out this diode currents and voltages, so we use these models to analyze the circuit, because like once we introduce a model, it's like it's a kind of a easy way to identify the characteristic or explain the behavior of the circuits, rather sticking into the Shockley equation, because this is a kind of exponential type of equation. So then you know that once these exponential functions come into play, it's hard to find the numerical values, because we have to take the log inverse and so on. So rather dealing with the Shockley equation, we can simply identify a couple of model which approximately explain the characteristic of the diode, and then we can apply those models to find out the currents and voltages of the circuit, or the behavior of the circuit, or to find out the output of the circuit. So next we will find out what are the possible ways of modeling this diode, and then move forward.